For our final project, Alex and I were interested in exploring an integer programming problem and decided to create a Sudoku solver. Just a quick introduction on what integer programming is. Integer programming is an optimization method where the variables are restricted to be integers. These are very common, and we face these types of decisions in our everyday life. For example, dieting and deciding which foods to eat based on calories or nutritional value. Budgeting is also another good one. You have to decide how to allocate money. That said, integer programming can create very large and complex algorithms. Budgeting, for example, can get very complex. You need to budget for everyday necessities such as groceries and your water bill and electric bill, but you also need to budget for longer term things such as a house or an apartment or buying a car. For those that don't know, Sudoku is a puzzle game that has been around since the 18th century. There are a bunch of different Sudoku boards, but one of the most common ones is a 9x9 board. That means that there are 9 rows, 9 columns, and 9 3x3 squares. The way you play is that each row, column, and subsquare need to be filled with a number between 1 and 9, and no number can be repeated. So no row can have 2 3s, for example. Sudoku is a pretty interesting optimization problem because you can't maximize or minimize the result. It's just a puzzle, like a normal jigsaw puzzle. All the pieces just have to fit together. There's also not one approach that is necessarily better than another. So how can we optimize Sudoku? Well, we created a Sudoku solver that can solve any n by n board of any difficulty. Our objective function is going to be to minimize 0 because we don't have any decision variables that we need to minimize or maximize. Our decision variables are going to be each cell on the Sudoku board. Let X be the cell on the Sudoku board, and I be the row, J be the column, and K be the submatrix. We also have several constraints for the Sudoku board. We have a cell constraint, so each cell must be in the set of 1 to n being an n by n or a perfect square Sudoku board. And n is the largest value within that Sudoku board. So for a 9 by 9, 9 is n, and 9 would be the largest value. We also have row constraints. So for each row, as I had stated earlier, no row can have 2 3s. And we have the same constraint for columns. Finally, we have a submatrix constraint, so we can't have 2 3s in a submatrix or any repeat of any variables. And we also have an integer constraint, so x has to be an integer and cannot be any less than 1 and cannot be any greater than n. The data that we used was largely from a Kaggle dataset that contained 1 million Sudoku puzzles. These were 9 by 9 Sudoku puzzles. We also found a few other Sudoku puzzles that were 16 by 16 and 4 by 4. We found the problem and the solution online. The Kaggle dataset also provided us with the problem and the solution so we could compare these later. The basic setup of our Sudoku solver is that we ingest data and convert it to 2D arrays. We then have it go through our constraints and then our problem, and then we construct a user-readable printout and compare it to the correct solution so that we can see if our solver is correct.
As Julie mentioned, we have a particular use case where we actually were able to find a Kaggle dataset which had 1 million solutions as well as their initial problem. And so we had to derive some helper functions here that actually would account for that. We can't just generate a LP problem. We also had to create a kind of test framework for that LP problem. And so here we have 4 validation and helper functions that actually really helped along the way with that that use case. And so in the first function, we have just a very brief function that actually splits our Kaggle data set between quizzes and solutions. Then we have a function that actually takes the string input that the Kaggle datasets provide and convert them to the 2D array input that we expect within our LP problem, in this case an IP problem. And then we have a couple validation functions. One checks to make sure that our output, or in this case it says input, matches the expected solution, and it will return true or false. And then lastly, we have a validation function that takes the input array and actually determines whether it is a valid n by n matrix. So we have a perfect square. If not, then it will reject it and say that this is not something that we can solve. Moving along, we define some constants. In this case, we have values, and we define what the value constants can be. In this case, it'll be 1 to n, where n is, for the Kaggle data set, for instance, 9. But we can define this to be any number, depending on what you pass in. What our row constants and column constants are. And then we actually define our subsectors, and we define them. This is where we said submatrices in our definition above or previously, but that's what we return here. These are the constants that we allow for this particular IP problem. We take these constants that we have generated and we define constraints, and so we pass those things into this function, and we're generating constraints for whether it's rows, the values for the rows, the values for the columns, or the values for the submatrices. The constraints there are mapped, and then we also have individual cell constraints that are mapped here as well. Lastly, we take in the input problem defined by Kaggle, or in our case, we've defined also some 4x4, 16x16 matrices, and we process those with the constraints that we defined earlier, and it returns the problem that has been solved. And what we also get is, when we're looping through the 1 million different problems that Kaggle provide, we also have an exception that's raised if for some reason we find a problem that's either infeasible or was not able to be solved because of pulp. But in this case, we were able to solve all 1 million Kaggle problems and return that solved problem to our next function. We then have a function that actually constructs the solution matrix for that pulp problem. And with that, we're able to pass it into the previously mentioned helper function, where we're able to do some sort of comparison against the expected problem. And so when we have two 2D arrays, one is our provided solution and the other is the expected solution, what this allows us to do is do a comparison, make sure that they are equivalent. And if they're not equivalent, or we want to see what the output is, we also have a pretty print solution function, which actually takes these expected solutions and our provided solutions and prints them out to the screen so users can see them. And so what you see here, for instance, is a 4x4 problem and a 4x4 solution. And so the first one is the input, and we are able to print it out so that it's human readable. And then we have a 4x4 solution, and we're able to print it out so that it is human readable. And what we were able to determine was that whether it's a 4x4, a 9x9, 16x16, we're able to successfully solve any Sudoku board that is provided that is also valid in our set of constraints. We acknowledge that there are limitations to our current approach. We only gave 100% confidence to our 4x4, 9x9, and 16x16 approach. However, given how similar they are to the 25x25 and 100x100, we believe our abstracted approach can, with high confidence, solve those problems as well, or any standard n-by-n Sudoku board. That said, what our future problem sets can include are things that are a little bit more complicated than your standard n-by-n matrix, such as a Kakaru, or as you see here, a 5-in-1 windmill pattern, which are not n-by-n in any sense of the word. And so with that, we'll provide our references and also open up the floor to any questions. Thank you.